specific heat and calorimetry. In this session, we will explore several key topics related to thermal physics. We will begin by examining the relationship between internal energy and temperature. From there, we will define heat capacity and specific heat, which help us understand how different materials respond to energy transfers. We will also discuss the technique of calorimetry and how the principle of energy conservation allows us to measure thermal properties. Finally, we will go through two worked examples involving a silver bullet impact and the cooling of a metal ingot to see these concepts in action. When energy is added to a system, it typically results in a rise in temperature, provided that the system does not perform work and no phase change occurs. However, different substances require different amounts of energy to produce the same temperature change. For instance, raising the temperature of 1 kilogram of water by 1 degree Celsius requires 4,186 joules of energy. In contrast, 1 kilogram of copper only requires 387 joules for that same 1 degree change. Fundamentally, temperature is related to the internal energy of the molecules within the system, meaning that as we add energy, we are increasing the microscopic motion of these particles. We define two important terms to describe how materials store energy. Heat capacity, represented by A capital C, is the amount of energy needed to raise the temperature of a specific sample by 1 degree Celsius. We express the energy transferred as heat capacity multiplied by the change in temperature. Specific heat, represented by A lowercase c, is the heat capacity per unit mass. This property measures how thermally insensitive a substance is to the addition of energy. We can calculate the specific heat by taking the energy transferred and dividing it by the product of the mass and the change in temperature. Therefore, the total energy Q is equal to the mass times the specific heat times the change in temperature. It is essential to follow a consistent sign convention when calculating energy transfers. The energy Q and the change in temperature are considered positive when energy is transferred into the system, and they are negative when energy is transferred out. While Q often represents heat, a change in temperature can be caused by any method of energy transfer, such as work or radiation. For example, if you repeatedly bend a wire coat hanger, its temperature increases because you are performing work on it. While specific heat can vary slightly depending on the temperature, we often treat it as a constant value when dealing with relatively small temperature intervals. Calorimetry is a practical technique used to measure the specific heat of a substance. In a typical experiment, a hot sample is placed into a vessel containing cold water. We then measure the final equilibrium temperature of the mixture. This process relies on the conservation of energy. In an isolated system, the energy leaving the hot sample must be equal to the energy entering the water. Mathematically, we state that the energy gained by the cold part of the system is equal to the negative of the energy lost by the hot part. This negative sign ensures that our energy balance remains consistent with our sign conventions. To perform a calorimetry calculation, we set up an energy balance equation. Let the mass and specific heat of the water be represented by M sub W and C sub W, and let the mass and specific heat of the unknown sample be M sub X and C sub X. The energy gained by the water, which is the mass of the water times its specific heat times the difference between the final and initial water temperatures, must equal the negative of the energy lost by the sample. The sample's energy change is its mass times its specific heat times the difference between the final temperature and its initial hot temperature. For the most precise results, the container itself should be included in the calculation, unless its mass is small enough to be neglected. Let us look at an example involving a silver bullet hitting a wall at 200 meters per second. In this scenario, we assume the kinetic energy of the bullet is transformed entirely into internal energy. By setting the change in kinetic energy plus the change in internal energy to zero, we can derive a formula for the temperature change. Specifically, the change in temperature equals the square of the velocity divided by 2 times the specific heat of silver. Using a specific heat of 234 joules per kilogram degrees Celsius, we find a temperature increase of 85.5 degrees Celsius. Note that this result is independent of the mass of the bullet. In our second example, we cool a hot metal ingot. A 0.05 kilogram ingot at 200 degrees Celsius is dropped into 0.4 kilograms of water at 20 degrees Celsius. The final equilibrium temperature is measured at 22.4 degrees Celsius. To find the specific heat of the metal, we rearrange our energy balance equation. The specific heat equals the mass of the water times the specific heat of water times the water's temperature change, all divided by the mass of the ingot times the ingot's temperature change. This calculation gives us 453 joules per kilogram degrees Celsius. Comparing this to standard values, we can identify the metal as likely being iron. In summary, specific heat is a fundamental material property that defines the energy required to change the temperature of a unit mass. The basic equation for energy transfer is Q equals mass times specific heat times the change in temperature. Calorimetry allows us to use these principles, along with the conservation of energy in an isolated system, to determine unknown thermal properties. Finally, we should note that water has a very high specific heat. This characteristic is why coastal regions near large bodies of water often experience more moderate climates compared to inland areas, as the water can store and release vast amounts of energy with only small changes in temperature. To conclude, consider these review questions. First, why exactly does the high specific heat of water result in milder winters for coastal regions, such as the United States West Coast? Think about the direction of prevailing winds and the transfer of energy from the ocean. Second, in a calorimetry experiment, why is it mathematically necessary to include the negative sign in the conservation of energy equation? Consider how the final temperature compares to the initial temperatures of both the hot sample and the cold water, and how that affects the sign of the temperature change for each part of the system.